too many years ago, in the early 90s, this beautiful integration of physics and biology, where physicists were not simply there to put a number on known phenomenology. I was inspired by actually Professor Brochard, Dejean, and others who were looking through basic principles to bring about truly new insights in the biological context. And you'll see that actually what I'm going to present today is, I hope, one such example where concept of condensed matter physics, of phase transitions, really are the guiding principle to understand that phenotypic switch cancer cells, we believe, undergo as they not merely proliferate in an original site, but switch to a migratory and invasive phenotype. And how cells can do it is very much grounded in physics principles, as hopefully I'll convince you of. So again, thank you very much for this kind invitation. And without further ado, let's switch to the presentation itself. So I'd like to declare a conflict of interest. I'm a co-founder and investor in AbMeta, Ab for antibody and Meta for metastasis therapeutics incorporated. So I think I don't need to convince this audience that really a central problem in oncology and for too many cancer patients is that at the time of diagnostication, as screening has improved, the time of diagnostication, typically people have some metastatic spread where cancer cells have been able to spread from a primary organ of origin to distant organs. Many of you study metastatic disease, and there's good reason for this, is that metastasis is responsible for 90% of death from solid tumors. And it's remarkable how little we know about metastasis. There isn't an epigenetic signature of metastasis. There isn't a genetic signature of metastasis. There isn't a proteomic signature of metastasis. That is, if you take cancer cells, collect them from a primary tumor, and if a patient has had, say, a breast cancer patient has had spread to the lung, to the bone, you assess those cells as well. There isn't a priori anything special from a protein point of view, from a genetic point of view about those cells. And yet, clearly cells acquire new phenotype to effectively break down the basement membrane that confine cancer cells at primary tumor site to then spread to distant organs. We've made, well, oncologists, clinicians have made huge progress in first really catching tumors earlier and earlier. Actually, it has become more challenging to have access to those tumors because they're getting smaller and smaller, and really primary recipients for those tumors should be, and as it is, pathologists, where localized disease leads to high survival. The problem comes about when these assessments are made and detection is made when there's been already spread. Then 5-year survival dramatically decreases. We're going to focus specifically on triple negative breast cancer, which is the subtype of breast cancer where the outcomes are the worst and where there's no real specific treatment. Triple negative breast cancer patients will undergo standard of care that involve very old drugs that simply are mostly palliative and doesn't increase survival at 5 years. We're going to also focus on pancreatic cancer, and this is opportunistic. It turns out Hopkins is very strong in pancreatic cancer, and I decided to take advantage of that for our development and our studies. So really the fundamental question I'm asking, as I said earlier, is really how cells that are initially have acquired enough mutations to be proliferative can somehow, quote unquote, if I want to be anthropomorphic, decide to switch from this confined proliferation to a proliferative, to a invasive and migratory phenotype, where they break this basement membrane, undergo intravasation, and then they on their way disperse either through lymphatics or through blood vessels to distant organs. So some of you study vascularization, some of you study also the role of immune cells in promoting progression of this tumor. But what we ask, whether cell intrinsic properties cells would acquire somehow, as they would be all of a sudden able to now break down this confining base membrane at the bottom here and negotiate this collagen-rich stromal matrix between the base membrane and the freeway that constitute the blood vessels for effective spread. So just 1 second, that's a phone. I'm going to have to turn it off. So that's funny. So again, the question we're asking, what makes cells and what prompts cells to switch from what we could call confined proliferative state to a invasive and migratory one. So like many others, we initially studied migration, a key step in this metastatic cascade, again, to negotiate this collagen matrix in 2 dimensions. That is, we forgot for a moment, many of us, that we were substituting convenience for physiological and pathological relevance. And the reason was that you can use high power microscopes, many assays like atomic force microscopy for biophysical measurement, or even Western blot are so much easily amenable to for use when cells are just human cells, I'm talking about, plated on a cover slip. These cells will migrate by exploiting contractile stress fibers, typically mostly lining up the basal surface of the cells. You have this somewhat artificial apical polarization of the cell that really, of course, doesn't exist when those cells are fully embedded in a 3D matrix the way they are as they now leave that primary tumor site. You have focal adhesions that at the terminal ends of each of those stress fibers. You have a nucleus that simply seemingly passively moved around at the back of the cells, and the cells are naturally polarized until they ask themselves, what am I doing in that direction? And then undergo some new steps to undergo so-called random walk migration. So a lot of work has been done assessing the role of lamellipodium-specific proteins, such as ARP23, the role of focal adhesion proteins, the role of stress fiber, etc. Our view is that we had to move cells to the 3rd dimension, acknowledging the physiopathological reality that cells will have to negotiate the 3D collagen matrix. And so this is a little bit, in a way, what we study as a main platforms. We put either primary or cell lines inside a collagen matrix, not as trivial as it may look like. This is reflection confocal microscopy, where we can not only look at the cells, but also look at this very interesting coordinated deformation of the collagen matrix. But leaving that aside, the cells know that same cell you saw in 2D, this was an artist rendering of the cell in 2D, is now placed in a 3D collagen matrix, will first of all look a lot different. The lamellipodium disappears. The stress fibers that were mostly connecting focal adhesions and through integrins, the extracellular matrix on the plasma membrane are now connected to the nuclear envelope through link complexes that Andreas talked about. The lamellipodium is being replaced by interesting dendritic protrusions. ARP23 retains a role in producing these dendritic protrusions, but is not there to promote dendritic filament assembly at the lamellipodium, since the lamellipodium has now disappeared. The nucleus that plays essentially no role in 2D migration start playing a central role in 3D migration by providing mechanical support to those what we call actin cap fibers, that are hypercontractile fibers that, as I said, connect the nuclear envelope and promotes mechanical support to those protrusions, key to effective 3D cell migration. So I'm not going to talk much about this, but this is the starting point. Oh, one last point is that not only the structures are different, but metalloproteins that played no role in 2D migration start playing, especially those membrane bound, start playing a central role in 3D migration, promoting some partial digestion of these collagen matrix to then, through forcing through the actin cap fibers connected to the nuclear envelope, for net progression inside the 3D matrix. Fine. So what we're asking, in a way, is a physical question. And you'll see how density, for the physicists in attendance, the mother of all order parameters, right? If you look at magnetism.
Mieux que moi quand même, mais...
I'm sorry? I heard Françoise. So I call it the mother of all transition because in physics and chemistry, right, it's called concentration, chemistry, more density in physics. It's the parameter that will control the state of matter. For currents, of course, for water, from solid to liquid to gas, density is the parameter that at a fixed temperature, fixed temperature and pressure will guide the state of the matter at hand. Well, really, at least at a conceptual point of view, this was what guided us, our ideas. And you'll see that we can now couple tumor growth to metastasis in a way where density plays a central role. How so? Well, the observation really stemmed from a simple, the study stemmed from a simple observation, right? And you can do this in your lab today, right? You place cells in a 3D matrix. And if you care to monitor them for long enough, of course, those cells will start dividing. So of course, in a finite volume of your well, the density is going to start increasing. And we asked if it mattered. Okay? So this is human fibrosarcoma cells. Same thing will happen many types of cancer cells, moving around at very low density at some nominal velocity of around 0.2 micron per minute. The same cells will, over time, divide. And you'll see, first of all, its morphology will change, and the cells will move a lot faster. If you squint a little bit, this is low mag microscopy. I'll tell you in a moment why. You have many more protrusions, and as I said, the cells move a lot faster. Very simple observation. If you now look, you zoom back out, and you look at many cells, you'll revisit all movies, and you'll see that where cells happen to be in close proximity with one another, they'll do move faster than cells that happen to be far apart from each other. Okay? So from that observation, we ask, all right, over time, is indeed cell migration speed increasing? So this is as cells proliferate, and the coupling between proliferation and migration. Of course, if you simply more cells per unit volume in your finite volume well, you're going to see those cells indeed at some threshold time, really that correspond to threshold density, will start moving faster. Okay, interesting. And we can, we can be a little bit lazier here and simply seed a matrix with just increasing density of cancer cells. These are fibrosarcoma cells, HT180, which are routinely used in cell migration studies. And you can see that for increasing density, past the threshold density, these cells will all of a sudden move a lot faster. Okay? If you do a rigorous assessment of migratory parameters, like persistence, diffusivity, both persistence and diffusivity actually increase. So corollary to this, we see an increase in the number of protrusions, these famous dendritic protrusions I mentioned earlier being increased. There's a nice correlation that for an increasing number of protrusions those cells produce, you have an increased number of density. Again, the parameter here is simply density. It's the same cells in the same matrix, just more of them, making the cells more protrusive, and therefore more migratory. You'll see that actually at the proteomic level, those cells couldn't be more different. Now that's a showstopper, because if the phenotype of cells, that's the gene expression of those cells, mainly changing density, it puts in question many studies, and I'll go back to this. And you'll see this is drug response, migration, proliferation, all becomes changed as density changes. So is it the case in 2D? It's not. Indeed, as you increase the density of those cells, keeping in mind the distance between cells we observed in 3D, right, so as to compare apples with apples, for increasing density, for decreasing distances between the cells, cell speed decrease in 2D, right? Remember, it increased in 3D. So if cell speed in 2D and 3D were quite similar at low density, they start diverging for increasing a number per unit volume, right? Mind you, at those distances, you're still having cells far apart from each other. Those cells are not migrating, more and more slowly, mainly because they're touching each other. We're not talking about contact-inhibited migration or contact-inhibited increased migration in 3D. No, these cells are far away from each other. Of course, you ask, is it a general observation? We observe this in many types of metastatic, typically post-EMT, post-epithelial mesenchymal transition cells. Cell lines like MDA, MB231, which are commonly used in breast cancer cell migration studies or proliferation, because they proliferate a lot and migrate readily, you'll see the same thing. For increasing cell density, the cells move faster and faster. If you move to primary mammary carcinoma cells, same story. Low density of a basal cell migration speed that increase for cell density. Again, this is the same cells, nominally at least, we look at your vials, the same cells put in the same matrix, but now at different densities. Mind you, either quote unquote normal, you can call them non-cancer epithelial cells, or non-metastatic breast cancer cells do not show this density effect. This is the case of MCF7 cells. It's also the case of fibroblasts, right? These specialist migration cells used extensively, of course, in migration studies actually do not display this density effect, right? And these MCF10As are normal, quote unquote, normal non-cancer epithelial mammary cells, do not show the same effect of density effect. Of course, is the other key driver of tumor progression besides potentially metastasis, which we're going to study based on this observation, is proliferation. Actually, if you seed cells at different densities in a 3D matrix, proliferation rate doesn't change. Right? It's not because you're starting off at a high density that you'll see a faster rate of proliferation of the cells. Right? So it's a purely 3D phenomenon, number one, and two, only affecting one of the two main drivers of tumor progression, that is cancer cell proliferation. All right, so I'm gonna use a big word here, I call Crown sensing of mammalian cells, or Crown sensing is the ability of bacterial cells to sense each other at a distance to control each other's rate of proliferation. I'm gonna show you in a moment that we believe metastatic breast cancer cells, and of course, many other types of cancer cells, prostate cancer cells, pancreatic cancer cells, have the same ability that is really non-existing in normal cells, doesn't exist in 2D. Right? Before that, I was rooting for physics to win the day, meaning that I thought initially the way by which these cancer cells far apart from each other could communicate with one another would be, of course, through tugging, physical tugging of the collagen matrix surrounding these cells, right? So what could modulate cell migration speed would be things like fiber alignment, which in separate studies, we and others have shown would increase cell migration. But if you increase cell density, if anything, but of course the correlation factor is just too small to conclude, but fiber alignment barely changes, as it should, right? There's no good reason why having more cells in your gel should somehow increase fiber alignment, even over time. Same thing for the interfiber spacing. If you will, pore size of these collagen matrices is not much change for increasing cell density, and if anything, change in the wrong direction. Pore size decreases for increasing cell density. So clearly, parameters of this matrix, stiffness, by the way, doesn't change either, that could have been responsible for the cell density effect of increased cell migration are not possibly the reason behind this effect. So we embarked on something, or before that, we embarked on something that usually, well, you don't want to get started on, which is to try to identify if it's not somehow matrix remodeling that is responsible for this cell density increase and migration, right? Then it's biochemistry, right? And we did, of course, the first experiment that comes to mind as a way to demonstrate that maybe secreted molecules are responsible for this effect, which is to take the supernatant from matrices containing a high density of cells and place this supernatant on top of matrix at low density. Again, same cells, same matrix, we're just moving the supernatant. And long and behold, this conditioned medium, CM, when added to cell at low density, fully recapitulate this increased cell migration observed at high density. So seemingly, there's something in the soup there that is present and sufficient to produce this observed increased cell migration, right? So it's not physics, seemingly it's biochemistry. And as I said, try to identify what could be responsible for this is a heron's fool typically, but we were a bit lucky. We were lucky in that we were able to work with a good friend, Rong Fan, who had developed a few years earlier a digital platform to, in a mostly agnostic way, compute, really measure the level of secretions of preset factors, including epidermal growth factors, EGF or PGDF or VGF, and a bunch of interleukins. So we were lucky not only to know Rong Fan and his platform, but also that the 44 proteins that were available for its platform, it needs a lot of tedious validation to be of use, turned out to be a subset of them to be the molecules responsible for this increased cell migration. So as you can see, for increased cell density, both for human fibrosarcoma cells on the left and MDA and B231 on the right, interleukin 6 and interleukin 8 light up, right? Little movement, so to speak, little activity of increased production of EGF or FGF, some potential cytokine or growth factors or chemokine that could have been increased and maybe potentially responsible, TNF alpha, TNF beta, are not changed for increasing density. What is changed, though, remarkably, is interleukin 6 and interleukin 8, IL-6 and IL-8. Of course, the next question was this causal? Correlation doesn't make for a cause and effect relationship. So we asked, are IL-6 or IL-8 or both potentially responsible, necessary, and sufficient indeed to produce this enhanced migration at high density that we did observe, right? So first, we validated these measurements with a simple independent assay and indeed showed that IL-6 and IL-8 are increased for increasing cell density, okay? So his single cell platform, it's a remarkable platform which can assess a secretomic profile at single cell level, but is mostly kind of a discovery platform, was indeed validated and found that IL-6 and IL-8 were dramatically increase in production, still nanogram or picogram per milliliter level, but were increase in production or in secretion for increasing cell density in these 3D matrices. Mind you, none of this happened in 2D. No increase in cell migration, and indeed no increase in the production of IL-6 and IL-8 in 2D. All right, is these IL-6 and IL-8 necessary? So the way to assess if molecules are necessary for phenotype, in here, enhanced cell migration, you can start with functional antibodies, right? Where we treated our cancer cells with an anti-IL-6 antibody and anti-IL-8 antibody. And you can see minimal effect at low density, but indeed cell speed was reduced back to low density values when those cancer cells were treated with these functional antibodies, IL-6 and IL-8. So seemingly IL-6 and IL-8 individually or independently are both necessary for these rather remarkable enhanced cell migration observed at high density. We also knocked down IL-6 and IL-8 themselves and found the same effect. You knock down IL-6, you do not see anymore this high cell migration speed observed for control cells. Same thing for our IL-8 knockdown. Okay, so we conclude that IL-6 and IL-8 are seemingly both necessary to produce this enhanced migration observed at high density. Are IL-6 and IL-8 sufficient now? So the way to do this is simply to supplant, if that's a word, IL-6 or IL-8 or both to cells at low density. So here, again, we're adding purified recombinant IL-6 to a cell at a low density and actually observing no enhanced migration. Same thing, IL-8 alone. But when combining IL-6, IL-8 at the physiological levels observed earlier at this picogram per milliliter and actually in a molar ratio of 50-50, we observed, and this is recombinant MRM, we see observed this increase in migration observed both when we observed when using the supernatant and also observed at high density. You can actually see the same thing not only for fibrosarcoma cells and MDMB231. What you can do, of course, is to knock down the receptors for those molecules, or simply knock down IL-6 or IL-8 and pick up the supernatant, and you'll observe that indeed both IL-6 and IL-8, or simply treat your cells at high density with at low density with this combination IL-6 plus IL-8 combo, and then treat your cells with either IL-6 functional antibody or IL-8 or combination antibody. In conclusion of those different experiments, we can say that both IL-6, IL-8, and actually the corresponding receptors are both necessary and sufficient to observe this enhanced, induced, increased cell migration effect we observe for metastatic breast cancer cells and fibrosarcoma cells. I mentioned receptors. Here, we're knocking down receptors, and I'll preview the result a moment ago. You indeed observed an inability of these cells at high density to move fast because producing many protrusions when knocking down the receptor for IL-6 and the receptor for IL-8. Okay. By the way, we had observed prior to this that those cancer cells at high density express high level of the receptor. Right. So I've already told you that these cells produce more IL-6, more IL-8, but also more IL-6 receptor and more IL-8 receptor. Right. So now the cells that nominally identical at low and high density, right, coming from the same vial, embedded in the same, rat tail collagen matrix, will have a different level of expressions of at least those soluble molecule and the corresponding receptors. All right. if you want to publish in a decent enough journals and convince your good biological colleagues, you have to go dig deeper into establishing mechanism. There's a funny dude in Israel, Odette, who perpetually make fun of this, where reviewers demand physiological relevance. Of course, physiological relevance is in the eye of the beholder. Crystallographers will say, if you don't know the crystallographic structure of your proteins, you don't know anything about anything. Biochemists will tell you, if you don't know binding partners, you've learned nothing, and on and on. So I'm a biophysicist, but of course, I want to be producing work of relevant to biologists. And so we had to go through, I guess, the tedious motion of assessing what could be beneath these receptors responsible for this enhanced cell migration. Turns out I'm being facetious here. We did learn something interesting, which is that, of course, the literature will tell you that IL-6 receptor and 8 receptor in terms of signal will converge to the JAK2 STAT3 complex, which then can move to the nucleus, and one of the proteins that becomes upregulated when STAT3 becomes phosphorylated and moves to nucleus is WAS3, a activator of the ARP2/3 complex, studied by many people in France. The ARP2/3 complex promote actin filament assembly. We knew that in 2D, but had found that in 3D promote this dendritic protrusion branching I talked about in my introduction. So all this work, they're color-coded through either drug treatment or knockdown, show that indeed the molecular pathway responsible for this increased dendritic protrusion generation and therefore increase in migration is IL-6, IL-8, the corresponding receptors, phosphorylation of JAK2 STAT3, increase expression of WAS3, which activate the ARP2/3 complex and promote the generation of these finger-like protrusions that promote this ability of cells to grab onto the collagen matrix and move the cells forward. Okay, so again, proliferation will be coupled to migration by producing increased cell density. If you are still confined in vivo by the basal membrane, you've not broken it down, you will produce and activate an autocrine signaling pathway that involves IL-6, IL-8, and downstream from it, the ARP2/3 complex that then promote migration. Not shown here is that we found that IL-6, IL-8 not only promote ARP2/3 activation, but also activate MMPs, those metalloproteins I talked about earlier, in particular MMP1, which promote and allow for then breaking down of the basal membrane, this invasive process. So it's not just migration, but invasion early on, following, again, increased cell density subsequent to proliferation of those cells. Right? So now we've, in a way, coupled the two drivers of tumor progression, cancer cell proliferation, and through increased cell density to non-migration and invasion. All right, so can these effects be druggable? In other words, can we start thinking about translating these observations to first in vivo validation and then clinical trials? So we in luck, because IL-6 and IL-8, of course, commonly studied molecule in a completely different context of inflammation. IL-6 in particular is being IL-6 receptor inhibitors, tocilizumab, Hoffman and Roche used to be Genentech, is a molecule actually now in the news because used in the context of COVID treatment, is a well-known and validated functional antibody that block the ability of IL-6 to block its receptor. We also initially use reparexin, a small molecule inhibitor produced by a small Italian firm called Dompe that also used in the context of inflammation, not very effective, to block IL-6 from binding its receptor, IL-8 receptor. So if you use 50-50 and molar ratio of these molecules, according to the binding affinity, you can actually completely block the ability of these cells to produce, to activate ARCT3, to produce protrusions, and then, I don't know if I show it. No, I don't want to eliminate this enhanced cell migration observed at high density. So yes, the same way we're able to do it more cleanly with knockdowns or functional antibodies, we can now, against IL-6, we can actually block receptors. The good news is that these are FDA-approved drugs. Two is that they are usable not only in vivo, but potentially in patients. Okay? So I should have mentioned before I studied it all that there isn't a single FDA-approved anti-metastatic drug, literally. So the #1 killer for breast cancer patient actually doesn't have any equivalent FDA-approved drugs. Inhibiting metastatic disease is always a byproduct of shrinking tumors. Right? You could call it obnubilation, the obsession, you could call it, of shrinking tumors has led, I believe, obscuration of what actually matters for more and more patients. As now we are able to detect tumors earlier and earlier, is metastasis. And as I said, there isn't a genetic signature of metastasis, there isn't an epigenetic signature of metastasis. So the usual tools like epigenetic drugs cannot be used. And metastasis is not a priori druggable. I think it's incorrect, and we can dig deeper as I describe our solution to this. But before that, before moving to in vivo assessments, we wanted to make sure that there'd be some clinical correlates about some of the molecules in our pathway. So I guess a second benefit of having mapped out this autocrine pathway in our studies. WAF3 and ARCT3, when overexpressed, lead to much shorter survival, as demonstrated in this. This is MetaBrick. This is for breast cancer, and our own studies for ovarian cancer. Right? You can see that in same thing, by the way, for pancreatic cancer, PDAC, we see that those tumors for patients who overexpress members of autocrine pathway lead to shorter survival. So potentially a companion diagnostic for treatment. All right, so let's move to mice. That was my first foray in vivo work. So it was very naive then, but I think we got it mostly right. So we're using 4 sets of mice, control mice, those injected in with tocilizumab, an anti-IL-6 inhibitor, riprexitin, a 98 receptor, and as we showed, T+R recombinant being the most effective of those single treatments. Okay. This is orthotopic. These are not PDACs yet. These are not, these are immunocompromised animals. But just as predicted from our in vitro studies, we found no effect of these drugs on proliferation. So we knew that high density led to increased expression of IL-6, IL-8, but we also knew that seeding density had no bearing on increased rate of proliferation. So just as predicted, we found that treatment of these mice that were orthotopically injected in the mammary fat pad with breast cancer cells didn't lead to increased cell migration and, to decrease tumor weight. That was not the goal. The goal was, of course, to decrease metastatic burden. What we found is that assessment of the lungs, but also of the bone, lymphatics, and others, led to decreased metastatic burden. We are assessing this because these are human cells. We can assess human cell content in these mouse humans. We're also doing image analysis of our lung slides. Long story short, we see a decrease in tumor burden, metastatic burden in the lung, in the liver, especially when treating our tumors, primary tumors. This is although treatment, the tail vein treatment. So this is global distribution. So we wait 6 weeks. I should have mentioned this. We wait 6 weeks for the cells to grow, and at 6 weeks, we know from pilot studies that the cells start spreading to distant organs. So we are basically blocking the ability of the cells to metastasize. All right, we asked those companies to play nice and see if they'd be interested in a clinical trial where we'd combine Reparaxin from Dompe and tocilizumab from Genentech of Mana Roche. We were anticipating problems, and indeed we were proved to be correct. Companies tend to hate when we combine drugs of different companies, and also see it as a potential threat for any future use of the drug. Tocilizumab is used right now in arthritis, not in oncology. And so bottom line, we failed at convincing them to work nice. Turns out there was a silver lining to it, in that I wanted really to move to a clinical trial in humans. And we have wonderful colleague, Liz Jaffe, rather famous for work in pancreatic cancer, ex-president of the American Association for Cancer Research, and Jimmy Spangler, a protein engineer extraordinaire who developed two new architectures of antibodies. One, BS1, in terms of knob in hole architecture with two arms, one targeting IL-6 receptor and the other one targeting the IL-8 receptor. And also BS2, where we have tetravalent as binding with two arms targeting IL-6 and two arms targeting IL-8. So bispecific the rage in big pharma, because they of course provide for high affinity. I'll talk about it and demonstrate it. Increased specificity, right? If you ever say only a monoclonal antibody, or God forbid a single small molecule inhibitor targeting a receptor, you may find over time that cancer cells will, in a way, kind of, how to say this, mutate around those drugs as a way to circumvent inhibition by these single binding agents. By doubling the pathways that you are targeting, the IL-6 pathway, the IL-8 pathway, we actually decreasing the ability of these cancer cells to circumvent treatment. Decrease drug resistance, and it's a single drug therapy. When you have combo treatment, you have a whole phase diagram of total concentration, but also molecular ratio of those drugs. We didn't have these problems. We have simply two arms, and we can go ahead and get started on this. So the first thing we did was to produce it, of course. It's very pure, and it produced like gangbusters in HeLa cells and HEK cells. So we were lucky there. There was no way you could predict this, but it produced a very large amount. So these are naturally humanized antibodies because produced with human cells. Okay. So the next thing is to demonstrate specificity. We producing HEK cells. These are human cancer cells that either are controlled, they don't have IL-6 and IL-8 receptors, or only produce the IL-6 receptor or the IL-8 receptor, or both the IL-6 and IL-8. These curves showed you that our bispecific antibody indeed can bind IL-6 positive cells, IL-8 positive cells, and of course do not bind IL-6 and IL-8 negative cells. Okay, I'll spare you the details, but we have an antibody that produces very high affinity and specificity binding these cancer cells when producing both IL-6 and IL-8 receptors. We also assessed level of affinity through a binding inhibition study, where you first treat your cancer cells either expressing IL-6 receptor or IL-8 receptor, both, and then try to compete out the bispecific by treating your cells with recombinant IL-6 or recombinant IL-8 or both. Long story short, we can then compute an affinity which is in the tens of nanomolar. This is an IC50 for binding affinity. We can look also at the IL-8 receptor, same story, really high affinity when assessed through these competitor inhibition studies. Okay, so we now had to go back to our in vitro assessments and found that indeed starting off with control cells on your left, moving a lot in 3D, when treated with either BS1 or BS2, found a dramatic decrease in the ability of cells to migrate. We can see that we, and I'll show you quantitatively, we did better when treated those cells with the combo of these pre-approved 5-year drug, tocilizumab and niraparib, right? We found the same story for fibrosarcoma cells. So again, when treated these cells with recombinant or bispecific antibody, greatly reducing the ability of the cells to migrate in 3D, okay? This is what the data supporting these qualitative trajectories, but importantly, and that's why I'm showing you the distribution, and you can see this to some extent from the trajectories. Not only are we able to decrease the average speed of those cells, but we somehow eliminating outliers. The few cells that move really a lot for control cells in 3D are basically eliminated. Those outliers are basically reduced to nothing. Those bispecific antibody, something we didn't succeed in doing when treating both with tocilizumab and niraparib, where we still saw outliers, are now eliminated, and we don't know why, through treatment with our bispecific. Right, so we now move in vivo, again, immunocompromised mice, and here's, I think, the real kicker. We found that I didn't tell you this, but when treated on mice with tocilizumab and niraparib, we had to use between 30 and 50 milligram per kg for finding, decreased metastatic burden. This is nothing special. What is special here is that when using our bispecific, we're able to greatly dial down the amount necessary to reach the same amount of metastatic burden, down to 0.1 milligram per kg. This is a 500-fold increased efficacy. This is a lot and very good news, because that means we need a lot less product to produce. That's good, but also leading most likely to much less side effect, because using a lot less for the same effect. So first, again, we're using to orthotopic models and found no effect as advertised of our bispecific, as similarly to our either monoclonal antibodies or T+R treatment, tocilizumab or niraparib. So these we produce separately monoclonal antibodies that in a way are a separate arm of our bispecific, found no effect on proliferation, and indeed dramatic reduce of metastatic burden as assessed both in lung, in the liver, when using a T+R treatment or BS1, BS2. Mind you, again, these are apples and oranges, because we're using a 500-fold decrease in the dosage for BS1 and BS2 compared to T+R, yet reaching the same level of reduction of metastatic burden. Right? Can we do the same thing with PDAC, that is patient-derived primary cancer cells? So now you either put PDAC straight in the mammary fat pad or subcutaneously. Here it's subcutaneous. So yes, we can do this, and T+R did the trick. But more importantly, we asked, can we combine our bispecific with standard of care, SOC, standard of care treatment? In other words, talking to our good colleague oncologist, it dawned on me, naive me, that I couldn't simply anticipate that patients would somehow abandon their current treatment and somehow magically start using a molecule. That would never happen, because they just don't do this. We talked to patients and oncologists, and they say, no way, Jose, they would ever do that. But we asked, would you use a combination treatment? If our antibody or bispecific is very safe, would you use it with your standard of care treatment? This is what we're trying to do here. So gemcitabine for PDAC, this is pancreatic cancer. I've made several changes on you. I've switched from breast cancer to PDAC, and I switched from orthotopic modeling to PDX modeling. But long story short, we found that a reduced metastatic treatment burden when T+R treatment was made, but also when gemcitabine was added to the cocktail. But, and this is important, with the added benefit of tumor shrinkage. I couldn't achieve this with T+R. This is the green curve, exactly as predicted. But when you treat now these PDAC tumors with gemcitabine, a commonly used treatment for PDX, which by the way has little effect on tumor shrinkage in human subjects, but when combined with our T+R treatment has this rather dramatic effect of reducing not only metastatic burden as shown previously here, but tumor burden as well. All right. So the volume is decreased, right? And the weight of the tumor is decreased as well. I'm not showing you this, but we're obtaining the same thing with a bispecific, right? All right. If you look at your tumors, you're going to see that this is a Pdx tumors harvested from Pdx models. You can see these are the control tumors. They're big, but interestingly, even though they're the same cancer cells in the same mice, you see huge heterogeneity in tumor size and weight of these tumors. When we treat, I really co-treat these tumors with both tocilizumab and riprexian that target IL-6 plus gemcitabine, much more uniformization of tumors, telling you that we've somehow normalized and uniformized the response of these tumors to cancer. We don't know why, but this is very good news. It means that most likely more human subjects would be responding to our treatment. So somehow gemcitabine does help marginally in tumor shrinkage, but doesn't do anything about the variability of responses. But when treated, when added to T+R, uniformize this response. All right, so what have we talked about? We talked about cell density. In other words, in the words of Jean-Paul Sartre, l'enfer, c'est les autres. You know, your worst enemy are going to be acquaintances, friends, and family members, right? That means if you proliferating as a cancer cells, right, you'll set yourself in motion, of course, leading to premature death. And we really believe that this very physical concept of transitioning, of phase transition from low density to high density is really critically important on this phenotypic switch leading to metastatic onset and spread. 2, drug effectiveness depends on cell density. I glossed over this, but T and R had very different levels of treatment in low and high density, and also 2D and 3D. Totally ineffective because, of course, those cancer cells don't increase the production of IL-6 IL-8 in 2D, but also the level of expression of the IL-6 IL-8 and of the receptor is critically dependent on cell density. There's many studies that are seemingly contradictory. There's a famous fight that has occurred for the longest time, how metalloproteinase may or may not matter in cell migration. When revisiting the primary data of those two fighting labs, you can see that these labs use completely different cell densities in 3D, which leads to completely different phenotype. I didn't show proteomic assessment, but these cells are completely different. And we've functionally coupled tumor growth to metastasis. Tumor growth leads to high density, which then over time leads to change of expression of these cytokines, and then eventually onset of metastasis. Combination of FDA-approved drugs led to decreased metastatic burden, and we're now developing develop, a bispecific antibody that does the same thing, actually a lot more effectively, and normalize not only this response of metastatic cells, but also of the tumor itself. So I'm acknowledging the wonderful work that started a very long time ago of Stephanie Fraley, who's now at UCSD, and really was the very first to really, I think, illustrate the critical importance of the dimension, the milieu these cells have to navigate. She found how focal lesion proteins were at very different function when moving to the third dimension, if you will. Hasini Jayatilaka, who's now at Stanford, discovered really painstakingly looking at these movies, and really had a kind of a aha moment where she observed that cells that happened to congregate for a moment moved faster than cells happened to be far apart from one another in the same tissue, in the same construct. And then Michel Carl, who was developing this bispecific antibody. And then some of the usual suspects in terms of funding, I mentioned Wang Fan, Liz Jaffe, and Jamie Spangler. Before moving this, because I'm a show-off, I'd like to show you a little technology that has nothing to do with what you just talked about, but really, I think, cool and could maybe trigger ideas in you and potential collaboration. What I'm going to show you is how we can serially cut tumors, stain them with traditional H&E stains, register those slides, and reconstruct the tumors in 3D in a way that leads to single cell resolution of large volume that is no equivalent, as far as I know, even using clearing and technique. So here's on the left, these serially cut sections, unregistered, and on the right, a little magic registration step for local and global registration. We recombine them into a jambon de Parme or jambon des Ardennes. We then trained AI algorithm to recognize different types of cellular and non-cellular tissue, like fat cells, islets of Langerhans. This is a pancreas. We reconstruct in 3D. We're taking this for a spin here. We're going to zoom in into a panim, which is a precursor lesion in the pancreas. We went from the centimeter scale to the millimeter scale, redecorating these panims with submucosa, showing again islet of Langerhans. The fat, this is all real. This is not some computer animation. This is the real thing in human tissue at volume of centimeter cube, and eliminating now this acinine fat to zoom in further now to get to micron resolution and demonstrate that all along we have single cell resolution. So we can, through 5 orders of magnitude in length scale, really map large volume of tissue in 3D. Some sort of modern age anatomy where we can really revisit old questions about organization of lesions and tumors, this time in 3D and human samples. Sorry for the divergence, I couldn't help myself, but hopefully get questions about the topic. Again, Andreas, thank you so very much for inviting me. This is such an honor, such a pleasure. Looking forward to questions.
Yeah, great talk. So I enjoyed it a lot. So I think we will have a number of questions. So maybe I can start with your matrix. I mean, so what's happened if you increase stiffness?
If you increase stiffness, same phenomena. Stiffness doesn't seem to promote more quote-unquote communications. And the reason is because actually secretion of these interleukins is not dramatically modulated by matrix stiffness. I wish it were. I'm a biophysicist. I wish stiffness did matter, but it doesn't. Organization of the matrix doesn't matter much because as you increase collagen concentration, you change pore size, you change fiber alignment and stiffness. Those qualitatively do not change the picture I painted for you. Yes,
I mean, so you know, there's the work of Peter Friedl with increased stiffness, where he where he observes strand migration and migration of groups of cells that are in fact detaching when you are increasing stiffness. So what's your take about this?
No, this is all correct, right? You have a cool modulation between single cell versus collective migration, all absolutely correct. The thing is that by the time the cell have not undergone migration, the cells are now expressing the proper receptors and interleukin and MMPs to embark on that journey, that first step, if you're in the metastatic cascade, to now spread. In a way, if you can use this early on and block, for those patients, for instance, who are diagnosed with metastatic burden, to prophylactically now use a drug in the future, could be a way to do this. No, there's no contradiction in both lines of work at all.
Okay.
The work I was disputing is his fight with Weiss on the role of MMPs in cell migration. He claimed MMP had played no role in it, and Weiss did so, but they were both right and they were both wrong. They just used different cell densities, which led to completely different phenotype. MMP expression and activation is exquisitely dependent on cell density.
Yes. Great. So what is, in fact, then the other question, what is the predominant factor? You have IL-6, IL-8. Do you need both together? Is one more important than the other? So what's going on?
So there's thousands of papers on the role of IL-6. You can look it up right now on PubMed, right? On the role of IL-6 in tumor and tumor progression. All of it related, mostly at least, to intercommunication between cancer cells and immune cells. It's an immune story. We purposely remove cells from the picture. Right? It's a cell intrinsic effect I described. IL-8 a lot less. It's a much more understudied immune cell. The full effect comes from blocking both, but undoubtedly IL-6 is the main driver. It's mostly IL-6, less so IL-8. But if you're a patient and you're asking for the best full effect, I think I'm going to sound like a salesman here, but you want to use a bispecific targeting both IL-6 and IL-8. Great question.
Okay, so what is then, in fact, the let's say the transcription regulation? Because you need certainly inside of the cell some driver, let's say hub driver, that will drive both. So have you identified that?
So it's STAT3 that is the transcription factor that then increase the expression of WAS3, an activator of APT3. Are there other pathways involved? You can see we inhibit metastasis, we don't fully block it. Clearly, there's, I think, parallel pathways that are also triggered in this cell density effect, no doubt about it. But clearly we're doing, we truncating a large chunk, if you will, of this metastatic burden by targeting IL-6, IL-8. I would never say that this is the only way and the only necessary to block metastasis. We're blocking the full density effect for sure, but yes.
Right, then we have a question of Ocean Martin. That is, she thanks you for your talk, and IL-6 is a huge family of cytokines. We are wondering which member you are analyzing of the receptors. Is this IL-6 receptor containing GP190 subunit or only GP130? So
I'd have to look. I should know this by now, and shame on me. All reminding you, all of you, I'm a physicist who dabbles in biology. I don't know. I do know that IL-8 is absent in mice, and so that made us having to produce a mouse bispecific, which was very arduous. And so in order to demonstrate the efficacy of a bispecific, we had to literally produce a humanized mouse. I won't get into this, it's a total nightmare. But IL-6 has at least an ortholog in mice. Functionally, it seems to do the same thing of promoting metastasis. IL-8 doesn't exist in mice.
Okay, so then I have another question of Violaine Moreau. Great talk, thanks. A clue about the mechanism of expression of IL-6, IL-8, IL-6 receptor, IL-8 receptor at high density conditions. So what's
again my only I guess I cannot add a lot more from what I've done, which was to show that indeed JAK2 STAT3 in a way expectedly, right? Downstream of IL-6, IL-8 receptors, everyone knows JAK2 STAT3 are present. I know it's not JAK1, I know it's not STAT1, but then lead to overexpression of just the right molecule, ARC2/3, to promote then eventually cell migration. But beyond that, when you do a proteomic assessment, I wanted to say this, and ask how many proteins are down and upregulated low versus high density. Again, this is the exact same MDA and B231 in the same collagen matrix, just at low and high density. It's hundreds of proteins become up and down really by a factor of more than 2. This, to me, gives me pause, because when comparing mutations, if you don't control for density, you're in trouble, because expression will change dramatically. It's as if you could say, compare CHO cells with those human cells. They're just as different, and yet again, nominally identical cells, right?
Okay, great. Then the other question that may I ask is for instance, if you look on PDAC, you know, PDAC is a a lot of matrix. It's a desmoplastic tumor.
Exactly.
So when you have it, when you look, for instance, on the transgenic mice with the KRAS driver and P53 background, so these tumors are highly desmoplastic. So the problem is how the drugs can reach this tumor. That's the problem.
Hey, what did I do to you? Absolutely correct. I think one can look at this stromal response in PDAC 2 ways. One, as a way to almost protect cancer cells from spreading, or protecting the patient from cancer cells from spreading, or most likely an inability of drugs to penetrate the tumor. Absolutely correct. No, we looked at syngenic models. What I've told you, I didn't want to show you the data because it's not, statistically properly done, but in our KRAS-driven tumors in PDAC, we see the same benefit of repurposing tocilizumab and bispecific. So that's mice, right? As Bert Vogelstein will tell you, we've cured cancer in mice many times over. The real test is us moving to human subject, but I do not know, with looking at not immune responses, the benefit is there. Treating, repressing these mice with PDAC mice with T plus R, tocilizumab peripaxine or bispecific, inhibit the ability of the cell to metastasize. That's the good news. But we don't know yet if there's an added benefit of now repressing inflammation. Is it beneficial, or is not diminishing the effectiveness of our drugs? Hopefully it doesn't, but I don't know the answer to that question for fully immunocompetent mice. We're doing this in breast cancer and in PDAC both.
Right. And then the other issue is also, so another issue, important issue, is that the IL-6 and IL-8 also will interact with endothelial cells and blood vessels.
Yeah.
So it's not the only target. And then also the immune system is impacted. So very complex. So did you check what's going on with the vessels in the tumors?
No, I agree. Once you know, these tumors grow so fast, right? So again, there's blood vessel formation can occur during the 6-week period in orthotopic models. We, of course, control mice see a lot more blood vessels, not news to you. I can say we see, at least assessing OH&Es and IHCs, any decrease formation of blood vessels. We don't seem to affect this. Again, another tumor microenvironmental effect that could be affected or not with our bispecific, with our cocktail treatments. That's another driver of tumor progression we're going to have to assess fully. We went straight for the jugular or for the slam dunk, whatever analogy you want to use, and assess if all bispecific continue to work in immunocompetent animals. The good news, yes. How? We don't know.
Okay.
That makes sense.
There is another question of Talita Santos, I think it's the right name. Great talk, thank you very much. My question, is there any difference in MIF expression between cancer cells and cancer cell lines analyzed? In your data, the MIF gene was also highly expressed.
MIF standing for?
Dr.
Santos? I don't know.
So I don't know now, but it's the
in secretomic profiling?
Secretomic, yes.
I don't think so.
It's a macrophage inhibitor factor.
Well, for sure, we were looking at the change in expression in cytokine or growth factors. Let me look, just 1 second. Apologize, once again, I'm looking at my own data. So MIF was not, right? So it doesn't change with density. So I can't say that would be a natural target for this density effect. And none of the other above either. So I can't say we were exactly motivated to look at MIF per se.
Okay, so that, so great. So so maybe again another question on your AI model. So how you compare, because you said your AI model for it's higher, it's the
better, meaner,
better than clearing. It's better than clearing.
So it's a long list of benefits.
Yeah, what's the
many, right?
Yeah.
So in no particular order, right? Number one, we are not limited in number of labels. So typically when one does, and that's the true competing technology, would be clearing and combined with light sheet microscope. We do that too. Once you've reached 3 or 4, maybe 5 labels, antibodies, that's it, you're done, right? So we, in the skin, for instance, we can look at 22 different labels. There's no limitation. Anything you can annotate by hand on H&E can eventually be used as a training to be automatically annotated. By the way, we can use intervening slides. We can skip 2, we know that, and do IHC or IF, meaning we can use antibodies to recognize B cells from T cells, from Tregs, from cytotoxic. So we then can train our algorithm to recognize in H&E those cells. And we've done that to distinguish B cells from T cells already. So second is that there's, like Levi-Strauss, it's called cumulative history. You never learn, having looked at a first tissue and clearing it and imaging it, the next tissue, you start from scratch. In using AI and H&E, we use less and less and less manual annotation when we move to the next sample. We indeed, many of our cells now automatically recognize without any additional annotation to train or retrain our algorithm. So it's cumulative history. Check it out. So number 3 is that we are, once you've cleared your sample, right, the tissue itself cannot be reused. That's it. H&E is for the ages, right? Once you deposit the digital images of those slides or these reconstructed, either way, they can be deposited, and new people in other groups can now use their own algorithm to recognize new cells and work from there. While in this transfer, again, it makes for nice movies, but doesn't make for really very useful information. And then exactly that, the last bit is that very little quantification can be done when you have cleared samples. Here, we had exquisite information about, for instance, spatial correlations of cells at the single cell level, right? For instance, immune cell penetration into tumor is often assessed in 2D, which is of course sacrilege, right? Because completely erroneous. Spatial correlation should always be done in 3D. The size of subtissues should all be done in 3D, but routinely done in 2D, right? We can do all of this in 3D. Again, if you do not label, say, your blood vessels specifically in your clearing, you're out of luck. You don't know where your blood vessels are. If you don't specifically label your ductal structure, you don't know where your ducts are, and on and on. We don't have that problem. So I think, oh, finally, resolution. We completely circumventing the central problem of microscopy, which is the Z resolution. Because we take scans, we have as high resolution that can be obtained through lateral scanning. We can do 100x resolution and get micron resolution. If you use light field microscopy, you don't have that. You limit it optically. We not, right? So it's brute force. You can say this, but it's incredibly effective. So I think there's many benefits to it.
That's great. So in fact, you train your AI algorithm the way that you can, in fact, project the algorithm on the standard HE slides and then pick up all the relevant, I mean, subsets that you want, because you have it trained in your algorithm.
That's right. So we literally interview a pathologist for a couple of hours, teaching us how to manually annotate, cancer cells, fat cells, endothelial cells, the stuff that they can do straight out of H&E that does not require antibodies. And off to the races. Anything that does require an antibody, such as recognizing CD4 positive T cells, for instance, we use intervening slides. We can skip 2, we know that.
Yes.
Do an HAC and do the same, recognize them. Here they are, we take an image and then train algorithm. So we not limited in volume, limited number of cells, we can limit in anything. And it's good old-fashioned H&E. You're in Paris, you're in Bordeaux, in Timbuktu, or Baltimore. It's the same H&E used everywhere by simple, pathological assessment. So it's extremely, I think, democratic, if you will.
I think that's really great. Okay, so I think thank you very much, because I think we have no more questions, and it was a great talk. Thank you very much. So maybe we can be more in contact also with some feedback in science. I mean all the other people too can join, and maybe for this AI technology would be great.
Yeah,
to have some interaction.
The antibody, we'd love to give it to you. I'm sure, as you pointed out, Andreas, for your own work, for others, IL-6, IL-8 is a well-known actor in many bad things, right? And so it can be used for other purposes. As I said, we are trying to see if it could be used in COVID treatment for acute cases. And then of course the 3D platform. For those, so we're starting to look at the eye in 3D, the skin in 3D. If you go on Google and type skin 3D, it's all cartoons. There's no one has ever actually seen the skin in 3D for real, no one. And so we can look at the brain, and the liver, and really at a minimum being used for instruction of med school students, because it'd be the first view of kind of the global centimeter scale view to the millimeter down to the micron scale.
So I would be interested if you would look on brain tumors, but it's the
GBM, right?
Yeah, GBM or low-grade glioma, stuff like this. So we have slides. So maybe
there's less, somewhat less if you mind me saying, interesting features, right? Ductal structures are not there, and blood vessels a little bit less also, which is make for less, how do you say, beautiful videos. But I think that GBM, many people somehow have asked us to look into this. If you provide us with serially cut tumor and a controlled brain, even better. In mice, this is not just human tissues we can assess, of course. We'd love to do this. A few tens of sections, we can tell you if it can be done. The magic sauce is really the registration. The registration was the tough nut to crack, which we did.
So you have to tell us exactly the conditions of the slides, how they should be cut, and then we will send them.
Totally routine. It's 4 or 5 micron. We don't want too thick. 4-5 micron is what I guarantee you pathologists use every day in Bordeaux. It's
you need just HE slides, right?
It's H&E. It's H&E. It's nothing special.
Okay, great. Okay, good. So great talk. Thank you very much. There have also many thanks. There's Shahad Al-Badri, who's many thanks for this fantastic talk and work. So this I would say also to you, and thank you very much, Denis.
Andreas,
keep in touch. Okay.
I will. Please find me an excuse to come to France. I'm a francophile, and so
yeah, we will be because when in October, I think, when from October we get rid, hopefully more rid of the COVID, then we will invite people here.
Yeah. No, I'm gonna make you all jealous. I'm already vaccinated, but don't tell anyone else. Yeah. It's
I mean, in France, it's terrible with the vaccine. You know, they are so late.
It's the worst in the world, just about.
It's the worst.
Belgium being even better, even worse. Sorry.
Yeah. Okay. So thank you very much, Denis.
Bye, everyone.
Bye. Thanks. Bye.
Thank you. Au revoir. Merci.
Stop.